Thank you, Sally, for inviting me. So the goal of the talk today is to do a data-driven exploration of how much flexibility do we have in loads, both residential and business. So this work had the participation of some of my students, my postdoc, folks from PG&E, as well as June Flora. So here's the quick organization of the talk. I'll have a very short introduction, and I want to jump in right away into various data-driven analysis of the potential for loads to offer services to the grid. Okay? So let's start with our introduction here. So utilities today face a new type of challenge. The penetration of renewable generation has increased variability and reduced revenues. So the current business model is not really sustainable for the future. And you can see this with the stories that are coming out today from Germany, for example. So on the other hand, there is an opportunity to mobilize demand-side flexibility. What does that mean? Well, I can start to pay and get service from a lot of these loads. Today, this is reserved to very large customers. But because of pervasive sensing, one example, smart meters, low-cost communication, and all kinds of new smart grid technologies, you have the opportunity to bring into the load side management small and medium-sized loads, which were not cost-effective to manage before. So what is the challenge to make these guys participate in the grid? So here is the three main questions that I would like to investigate. One, how to measure flexibility. What do I mean by flexibility and how to measure it? Two, how do I identify flexible consumers? And three, how to elicit flexibility through programs. So let me start with this last question. Today, the way flexibility is elicited in the grid is that customers enroll into programs. An example of a program is the Smart AC program in PG&E, so here in the Bay Area. You enroll into it, and the utility gets the right to send a signal to turn off your air conditioning. Okay? When a customer enrolls into the program, this process is done through a thing called program management, and that consists on the utility or the system operator or the platform contacting customers and inviting them to enroll. And this is typically what happens when this process is done on a population today. You have a measurement, which is the program benefit to the customer. And what you see is that people with large positive benefits typically enroll. People with large negative benefits don't enroll. And then you have these two classes here. People with small positive benefits, they fail to enroll typically because they don't realize their benefit. There's no good information for them. And then people with small negative benefits, if they change their behavior slightly, they would get the positive benefits and they should have enrolled, but they also fail to enroll. The performance of a program is measured by this number called yield. So yield is interpreted in two ways. There's one yield, which is the marketing yield. I contact 100 people, 80 people enroll, my yield is 80%. The yield that's more important, though, when you think about flexibility, is a quantity yield. I target a certain number of kilowatt hours of flexibility that I would like to achieve. I go and contact all these people, they enroll, and I see when I run the program how many kilowatt hours of flexibility actually were achieved. The ratio between those two is the yield, and unfortunately, yields today are pretty low. They're between 10 and 20%. So the question is, okay, if you want to elicit this flexibility of various types, I need to run these programs better, and to understand how to run these programs better, what can I do? So here is, let's see what is done today and what we are trying to do and others as well. Today, the way a program is run is you start with an initial small set of customers, say 100 or 1,000. You send them a bunch of questionnaires. And basically, in these questionnaires, you ask about their habits, family, and so on. Then you install the program, or you run the program including these 1,000 folks. You now have a before scenario and after scenario, which measures how much response you got in terms of flexibility, how many kilowatt hours you got from these people. And you try to build little models to estimate, okay, which other customers are likely to respond, okay? The problem with this is that the actual consumption and the actual response do not enter as a primary factor in designing these methods to identify the customers. So instead, what can we do? Well, the idea we propose is take instead 1 million customers, okay? Now I can observe their data through the smart meter. So I'm in a way measuring their behavior through this data. Now what I do after that is I create features. These features tell me something about each type of flexibility. So I can look at the data and, for example, calculate the thermal sensitivity of a customer. How many kilowatt hours does the guy change per degree Fahrenheit outside? This tells me indirectly something about their use of air conditioning. Using these features, I can now build response models. I can do segmentation, targeting, and even determine how to schedule the customer. And notice, I have this very large population. So I have I'm much more knowledgeable about what is going to go on. So this is initially done in open loop. Now you can enroll the first few customers into your program, or you can have them have a choice of technology. It could be a storage or EVs or so on. And now you can close the loop, because up to now you have been kind of driving blind or walking blind, because with the initial customers, I can actually see the response and build better models. Okay, so that's conceptually what we want to do. And to do that, we went and talked to utility, PG&E, and we obtained this type of data. We got about 218,000 homes. We got a year worth of their smart meter data, and we got about 100,000 small and medium businesses, and again, a year worth of data. One of the things that the data comes with is, for example, what is their climate zone? We also got temperature data, as well as, for example, their zip code. One thing I want you to observe is there is this coastal area here that it's marked with zone 3, and there is an inland area here, dry, zone 13. This will be important for the comparisons we will be doing with this data, okay? So what I did with this data is we built these feature-based models, and I came up with some data-driven estimates of flexibility potential, okay? So let me show you what these numbers look like. 60% of the daily load is variable. So you immediately see there's an opportunity for moving loads around, for example, peak shifting and all those kind of things, storage. 11% of the daily load per customer on average happens in the peak hour. So in that 1 hour, if you could change something, that's 11% of their load, okay? Storage and spreading this consumption over time can reduce costs both in the wholesale and for the customer themselves between 20 and 70%, okay? In particular, when we look at residential loads, one of the things we see is on typical hot days on an inland area, well, the total daily use of a customer is 33 kilowatt hours. On typical non-AC days, like a winter day or even summer in a coastal area, in a city like San Francisco, the daily total use is only about 8 kilowatt hours. Interestingly, all of the behaviors we see of customers can be described with 262 load shapes. A load shape, I'll explain later what it is. Each customer has about 10 1 to 2 hour blocks of 200 watt daily consumption. So you can imagine these blocks could be moved around using various strategies. And about 1 million homes can reliably provide 250 megawatts per degree Fahrenheit of demand response. So that's for residential customers. For small and medium businesses, we can do similar estimates. And the first thing we observed is that now there is no such distinction between a hot and an inland and a coastal area, or weather has much less influence. So they're about homogeneous consumption, and it's about 53 kilowatt hour average. For each industry, you need about 100 load shapes to describe the consumption. So can you imagine, if you have about 10,000 or so customers in an industry, and I only need 100 load shapes to describe their whole year worth of data. Okay. They have many more blocks of flexibility, and the amount of demand response these businesses can provide is quite small. It's on the same order as residential, except there is much less small businesses in number than homes. Okay, so that's an interesting insight. Okay, so what I want to do now is to show you how I arrived at these numbers. Okay, so let's start with this aggregate analysis. The first simple analysis or feature I want to extract is the base load consumption percentage average per customer. So I take the base load amount you consume every day, I average it across, I calculate the percentage of the total that corresponds to, I average it across the year, and I get a number per customer. Okay, this is what it looks like. Here I have the two different climate zones. This is a cool area, San Francisco. This is an inland, let's say Santa Rosa. And you can see here, both in winter and summer, typical base loads are around 40%. Okay, same for the inland area. Slightly less, indicating maybe you are starting to see some influence of air conditioning. So from this, I can say these are loads that are always on. So I get my number. 60% of the daily load is variable. I repeat this analysis for all of my SMB data. I get very similar numbers. Okay. The one difference between SMB, small and medium businesses, and residential loads is the magnitude. So here I just plotted the cumulative distribution function of the average base load per customer of all my small and medium businesses. And here I have for residential. These numbers are pretty close if I just take the residential and multiply by 10. So for example, the median small and medium business base load is around, or let's say 80% quantile is about 5 kilowatt hours. And here 85 is 0.5. Okay? So keep this in mind. Most of the results we saw, you can find the same behavior for businesses and residential customers, the same amount of flexibility, except you have to scale it by about 10 times. Okay? So now let's look at average daily peak. So what I want to do is, again, calculate it as a percentage of the total consumption and just plot a histogram where each customer gets a number. Okay? So here's what I see. The median is about 11%. Again, it's kind of independent of the season, independent whether you're coastal or inland. And that corresponds roughly on residential homes to 1.8, 1.9 kilowatt hours, and about 20 kilowatt hours for a business. Okay? So this indicates a large amount of flexibility for shifting peaks, for technologies that can slightly spread your peak. That can be done with small amounts of storage and even actual storage. Okay? Another thing I wanted to do was just to see when are these peaks happening, because that might tell me something about what these customers are doing and about additional types of flexibility. So here I looked at the residential customers. Here is zone 3. That is the coastal area. And here's a distribution of the percentage of time that the peak happens in each one of these hours. And I'm only looking at the afternoon peaks. You can see that in winter, peaks are happening early, and then in summer, peaks are happening late. This is coastal, not a lot of air conditioning use. Days are a bit longer, so maybe people are turning on the lights a little later. So this serves as an indicator of potential for lighting. And it also gives you this important information. There's a lot of peaking that happens after 6 o'clock in the afternoon, after kind of the sun is out. Now if you look at inland, where there's a lot of air conditioning use, the pattern is slightly different. During the summer, the peaks are happening earlier. Why is that? Well, a lot of homes pre-cool. Therefore, they fire that air conditioning at the home, and that provokes the peak. So that pushes the peak ahead. Okay. Another study we did, we explored this in a lot of detail for these small and medium businesses. And here again, I have the distribution across all the afternoon hours, the percentage of time the peak happened for these SMBs for each one of these categories. And you can see some interesting things. For example, manufacturing, it's kind of off by 6 o'clock. If I look at construction or retail, I have these later peaks in the day. And in fact, these correspond to the activities themselves. You know, they might be doing tasks later at night when it's cheaper to use power. And in retail, there are shops that are open late, for example. Okay? So you can exploit these flexibility, these opportunities, to determine how to do your programs. So now let's go to the next type of flexibility. One question that came up when we started looking at this was there is all these technologies that are looking into scheduling, right? Scheduling when you run your washing machine, scheduling your EV, or scheduling different forms of consumption. So we wanted to create a feature that allowed you to measure the potential for scheduling. Obviously, this potential may be smaller than what we show, but it's kind of an upper bound. The idea is very simple. Take your daily consumption and break it up into chunks of 200 watts. Because we believe, 200 watts is kind of a basic unit of a task. Okay? It's like 2 light bulbs. Now, count how many blocks of each duration you see here. So for example, this is 1 block right there. If I had arbitrary power to schedule, I can move this block around and place wherever I want. Okay? That's the idea. Here, I have a very long block that does not allow me to move very much. Okay? That's the basic concept here. Online, I also included a paper that shows you more accurate measures of scheduling, but when we run it on the data, we get very similar kind of behaviors. So here's what we did. We counted how many blocks each customer had of each length. We averaged these counts across the population to give you kind of a picture of how the different zones look like. And here's what you see. For example, for zone 3, typical customer has 7 blocks that last 1 hour and about 3 blocks that last 2 hours. Similarly here in the summer for zone 13, I have about 8 blocks here of 1 hour and then maybe a little bit more, maybe 3 blocks, 6 blocks or so, 5 blocks of 2 hours. So roughly what I can say is there's 10 1 to 2 hour blocks that you experience. So this is very exciting because you can see that all the long blocks are very infrequent, right? So there's a lot of possibility to move things around, okay? One of the questions is, well, these distributions were done based on kind of an average customer. So I took that count for each customer and I averaged them together. Are customers different amongst themselves? So here's what we saw. We ran kind of an algorithm that allowed you to distinguish typical curves, scheduling curves. And you can see there are customers who want a lot of small blocks. There are customers who consume a few larger blocks. And you have all these different types. So this was very exciting because there is this whole area of what's called duration differentiated services. It's a new area that has emerged on how to price electricity based on the duration of how much you consume. And this indicates there is support from the data to do that. And what we are investigating now is how to make these models a little bit more sophisticated to actually design the contracts around the data itself. The last thing I want to look into in the aggregate is really the daily total power consumption. So what I do is for every day, every customer, I sum the total energy and I create a sample. I look at the histogram of these samples. Okay? This gives me an idea of, okay, how much consumption there is in a zone or during a particular type of weather. There is a very classical paper that came in the 70s from Berkeley that says this histogram is supposed to follow a log normal distribution. Okay? And we actually did that. We looked into it as the log of the consumption. We plotted the histogram, and a Gaussian actually fits that data. So we are looking here into San Francisco, and we can look into summer, winter, and that's fine. Okay? So here I had the histogram, and here I have the fit on top of the actual data. So we repeated the same idea for SMBs per type of business, and we again saw the same thing. Maybe the mean and the variances are different, but still a single log normal distribution. see, that was the basis to say customers are homogeneous on their total consumption, okay? So up to now, in utilities and contract design, that has been the assumption. Now we looked at inland, and there we had a surprise. First, during winter, the distribution is also log normal, fine, and the parameters are very closely matching those parameters that we see in coastal areas. But if I look at the summer consumption, a single log normal fails to fit the distribution. In fact, what we see is that you have two log normals. Okay? One lower log normal, one distribution that has parameters very close to these. So these are potentially the days in which you are not using your air conditioning, or the customers who don't use air conditioning at all, even though they live in a hot and dry area. Okay? And I have a second distribution which is higher, consistently higher, and that's capturing the air conditioning use potentially. So this fits what's called a mixture model very well. And this proves, well, you actually have heterogeneity in consumption. That homogeneous assumption is incorrect. So when I'm trying to figure out flexibility potential, here is potential. Every day where you drew your consumption from this distribution, this green distribution, is a day where I could actuate on you and maybe get some flexibility, okay? So that was kind of a new result, which was not there at all in the literature, okay? So what we said is, well, the natural thing to do, given that we see things are not homogeneous, is to actually try to do a segmentation of the customers, because there is segments. Right there we saw one example. So here's the idea we had. We said, let's take residential customers to start with. Well, the load shape is the following idea. I take your daily consumption and I normalize out the total energy. Now I look at this normalized time series. Okay, so after I normalized, this will sum up to 1. Okay? And what I want to figure out is how many load shapes are there in my customer population. Because our idea was these load shapes represent the collection of actions that you do in your home. And since you normalized out the energy, we are in some ways normalizing out the size of your home and some numbers like that. And in fact, we can verify that statistically after we count the number of load shapes that there are. So what we did is we took these normalized shapes and we ran a special clustering algorithm that we built so it could run on a database that had about 66 million residential load shapes. And what this algorithm does is pretty simple. It tries to find a certain number of cluster centers so that every cluster only allows a finite and controlled deviation from the cluster center. So we specified that as a parameter. Okay, typically we found 20% is a good number. So that is about 1% error from the cluster center per hour. Okay? So we ran this algorithm on the whole data set, and we saw, okay, how many load shapes do I need to capture the whole population? So here's the curve. Here I have a curve that says the number of load shapes that I need to cover a certain percentage of all of my 66 million load shapes, where covering means, the load shape is within 20% error from this representative in the dictionary, okay? And you can see here, with 272, I can cover 90% of 66 million. So there's a very small number of load shapes, okay? And let's see what these load shapes look like. So when we visited PG&E, both in their literature and also in person, what they said is every residential customer consumes this load shape. It's called a double peak. In fact, when we look at the dictionary, this is much more diverse. There are people who peak, in the middle of the day. There are people who are peaking late at the day, maybe graduate students here, or so, and things like that. So the question was, well, how much actually matches your belief? You designed all your programs to extract flexibility based on this belief on the top left corner. Here's how much it matched. Actually, only 14%. So basically, no wonder a lot of your programs are not doing well because only 14% of the load shapes actually follow what you believe. And our idea was, well, these load shapes are a form of feature, okay? And we even have kind of a behavioral explanation for why these load shapes are a good idea. What we say is this: everybody has some randomness on their behavior, okay? But if I look across the population and across all the days, whenever you had a certain pattern which matched, maybe your friend or you yourself in the past, now I can collect it together and estimate that pattern, okay? And that's pretty exciting. We can also demonstrate all the properties statistically and all that. So for those interested in algorithms, you can look online. I posted the papers for some of these, but you can also talk to me afterwards. So one of the questions immediately that comes to mind is the following question. I consume load shapes. How many load shapes I consume? Because if I'm the type of person that is very strict, very orderly, clock-like, a Swiss guy, I'm going to consume one load shape every day. Every day, I will wake up, do the same things, and come back home at the same time, sleep at the same time, and so on. If you're more like me, from Brazil and so on, time varies. It has kind of elasticity in there. So I may, consume a higher variety of load shapes. So what we did was to create a segmentation mechanism where here I measure the number of load shapes you consume. I use this thing called entropy, but roughly the idea is 2 to the power of the number here is the effective number of load shapes you're consuming. So for example, this fellow here, consumes about 2 to the 2. That's 4 load shapes, okay? And on this axis, I'm putting the amount of consumption. I'm using quantiles, so it's kind of normalized. And now I can break this whole population. Every single one of those 200,000 people are showing up here. I can break them into various classes, okay? And the idea is you can use these classes to start targeting. Because you can say, well, heavy and stable consumers are very good for demand response-like strategies, where I send a signal at a particular hour, and I want that load to be available to respond to me. People who are very variable actually are good candidates for pricing or energy efficiency, where you send messages, and they can choose a different type of behavior, because they're already kind of naturally flexible. So we propose this. Right now, we are working on validating these ideas with PG&E in this case, where we actually run this in a population, and we target various programs. Okay, so again, various metrics of flexibility here. So the next thing I wanted to do is this. I want to group people according to the load shapes they actually consume. So before I just grouped load shapes. Now I want to say, let me look at your statistics of which guys from the dictionary you're consuming, and I can create, prototypical people. And my idea was, are there that many different types of people? And we called each type a lifestyle. And in fact, what we found is, there is about 7 to 9 lifestyles only. Here's an example of a lifestyle. Again, it's kind of a graduate student. All of his load shapes are peaking late at night here. Here's an example of a more traditional family, dual peak and so on. So that's very exciting as well, because now we can start to think about designing pricing and various schemes taking into account this. And that's exactly what some ongoing work tries to do. So then we said, now let's go to the small and medium businesses. What's the story there? Is there like a single big dictionary that explains the consumption of all the businesses? What we found is you need to build a dictionary for each market segment, retail or, for example, manufacturing, construction, food services. I just showed you 4 of them, and I picked 4 load shapes. And you can see they're very different from each other. For example, here's a typical shop, right? It opens up in early in the morning. It has some period of time in the afternoon, kind of where, things are slower, sun is setting, so the air conditioning goes lower. So it's like a double peak. Interestingly enough, construction has a lot of loads that are on at night, because a lot of construction actually goes on at night. So if you're recording that in your meters, there you go. Okay? So again, we can do the same type of analysis in terms of the variability of these shapes and so on, and come to conclusions such as, retail and food services are more consistent than construction and real estate, for example. Okay? And you can use this information to target. Okay, so now we understand there are segments, there are different behaviors, we have various metrics, there is opportunities for pricing and scheduling. The next thing I wanted to verify was, how much opportunity there is for a demand response, okay? And for doing that, this is the idea we had. We actually build a response function for each customer. This is the feature I'm going to extract, okay? And the response function measures your sensitivity to temperature as if you are only using air conditioning. So I have a reference temperature set point. Above that, I'm cooling at this rate. And below that, I'm heating at this rate. This model can be tweaked in many ways. It has been proposed before. For example, Tim Mount from Cornell uses it in a few economic analyses and so on. But the question that we had was, from this simple feature, can we already say something about the potential for thermal control? One type of flexibility, right? So here's what we found. Here I'm looking at zone 3. That is, again, San Francisco. You can see that, on average, you don't have much thermal sensitivity, okay? So that coefficient is very low. Okay? In fact, sometimes because of the noise in the measurement, you estimate it to even be small and negative, okay? And this matches up with the utilities' decision-making today. They look at San Francisco, they say, well, we shouldn't run any demand response or thermal program in San Francisco because it's not going to get a good response. On average, it's 0, okay? On the same vein, if I look at inland, I get a non-zero average. I have guys who have a lot of temperature sensitivity, how many kilowatt hours per degree Fahrenheit, and I have guys who have smaller, but on average, it's positive. In fact, we analyzed one initial set of selections that the utility did in a past program, and it really looks like you're randomly sampling from these two distributions, actually from the second distribution. So the effective numbers they're getting are very close to the average here, okay? Maybe slightly skewed to the right, okay? So then I said, well, but that's not very clever because, in fact, I can see there is some people with more potential. Maybe that has to be validated later on, but if I only had this data, I should use it, right? So here's the idea we had. We designed a selection algorithm. The algorithm is very simple. I have a budget of the number of people that I want to select. I have an estimate of their response. In this case, it's the thermal response, but it could be any type of response to a program or technology, okay? This response is random. It has a mean, it has a variance, etc. Okay, so it may have a distribution. So what the goal of this optimization is select n people so that the total response I obtain for the selected people exceeds a certain target that I set, and that probability of that happening is maximized. So I pick a target, I pick the number of people, and I run this, and it will give me the people who are most likely to allow me to exceed that target level, okay? The cleverness that we did here is this algorithm now needs to run for millions of people, so we designed a special form of actual algorithm to do this. And you can now, having a very fast algorithm, I can run it on those 218,000 people, 66 million days, and get things like this. So here is an example. In that inland area, I actually need, if I set my target to 2 megawatts, I need what, about, let's see, let me set it for 3 megawatts, and I need about 4,000 or so people to get to that, okay? And I can actually vary here, and I can see and get this nice curve. It's kind of consistent from hour to hour. We fit a separate thermal model for each hour. And that allows me to estimate that initial number, which I showed, 250 megawatts per degree Fahrenheit, okay? Now, if I look at zone 3, which was the zone with no demand response potential, if you remember, right? So the average was 0. I still get something. I need a lot more customers to get my same 3 megawatts, but I still get something. So this algorithm shows that. The interesting thing, we ran this for businesses, and we got very similar results, okay? So this curve now serves as kind of a fundamental measure of flexibility as well, okay? So the last thing I want to address is storage. And here's what we decided to do for evaluating the potential for storage. I want to start with something very simple. So today, there is what's called critical peak pricing. This is a retail program where customers are going to face a price that varies in time. Sorry for my block here. It's also varying in time, but this is the price. It's called off-peak during these blue hours. This is called partial peak, and this is the peak time. Typically, the difference between blue and orange top here is between 20 to 70%, okay? This program now has to be followed by all the businesses in California. They're all enrolled into this, and they're going to propose this for residential customers as well. The idea is that these costs also reflect the wholesale cost for the utility to contract power for you. Except they don't want to change the prices every day because you may not be able to plan and respond. So they kind of average it out over the year, but a different price per hour. So what is the idea then? Well, suppose I'm facing this. So now it's an advantage for me to buy storage, right? Because I could buy electricity here and use it during this time, right? What's the potential for me to save? This is a very simple calculation. Sum up all the power that you consume during this time, or all the energy, and divide by your total. It's a very simple estimate, okay? So I got this distribution. This is a cumulative distribution function, and I can read, for example, the median is for residential, 60% of my power is consumed during those peak price hours, okay? If you convert this, you can actually calculate roughly what's the savings you would have in your bill, okay? Depending on the pricing level, if you're in the 20% pricing level, that reduction is around 25%. If you're in the 70% peak pricing level, the reduction is around 70%. So it can be huge if I could buy all my peak hour power in the off-peak. Okay. Obviously, that's kind of hard to do. So you want to know whether, how much capacity of a battery do I need, right? The capacity of the battery is measured by the maximum amount that you consume during those hours. So here I plotted kind of a scatter plot. Right here is the capacity of the battery. This is you need to multiply these numbers by 100 here. But basically, this is the savings in the bill that you get. And these are all residential customers here. And you can kind of see some interesting numbers, right? If I pick any certain amount of savings, let's say 15%, I have a wide range of battery capacities. Or, looking at it another way, if I pick a certain battery capacity, there is a different range of savings for different people. So if I'm going to design a program that gives money for people to buy batteries for their houses, you could use this as a guideline. You can use this as an optimization and so on. Okay, but it's very simple curves. You can do an economic optimization. Okay. The next thing I wanted to calculate was there's a second part of the cost. One cost is the actual energy. Another cost is how much reserves and how much capacity of generation I need to keep online. Okay? So for that, typically customers are charged what's called a capacity charge, $6 to $13 per kilowatt. And here is the customer behavior model. See, the capacity charge is charged on the maximum of what you consumed over the whole month. Okay? So suppose that you change that maximum to the second highest value. So you were able to be warned in advance and you slightly spread out your consumption. How much can you save? So here's the curves. So typically, residential and retail very much look like this. If I change the maximum to the second maximum, I'm saving about 5% of capacity costs. If I now change the second maximum to the third maximum, closer to 10%. And if you can change, up to the fourth, so you're looking at the fifth maximum, savings are 15%. So this is pretty large for a very simple amount of behavioral modification. Okay. Similarly, you can see what happens, for example, for an SMB in construction. There are guys that don't really benefit at all, no matter how much I change. They're pretty consistent guys. And there are guys who can benefit a lot. So again, you could target them. Okay. The last question I had before my last slide was this. When you buy storage, the assumption is that you can predict how much you're going to use later. So you can forecast that and buy that amount. Because see, storage is not perfect. Each time I charge and discharge, I lose a certain amount of power. So there's a cost to that. So the question is, how easy or how hard is it to predict what I consume, right? Because if it's very hard, it's not possible for me to have an individual storage. So this is what we did. We looked up some data online. We kind of knew individual forecasting, gets you average forecast errors around 70%. On the other extreme, if I forecast about 10,000 homes together, that's a whole feeder. That's around, slightly less than 1% error, okay? So the question is, what happens in between? Here's me alone. Here is the whole, let's say, city of Palo Alto. What is there in between? Suppose if I had 5 homes together, 10 homes together, and so on. And this is the curve that we see. It's kind of a hockey stick curve, okay? And you can see that, for example, if I have 10 homes together, my error is already 10%. If I have 1 megawatt, that's about 100 or 1,000, roughly 1,000 homes, it's already 1%, okay? So aggregation reduces the forecast error. But that aggregation has a limit. It kind of tapers out here, okay? Then I actually decided to do one exercise, which was, see, the forecaster I used was very simple. I just used kind of an AR model, some standard forecasting setup. But then I decided to say, there is all these forecasting algorithms on the literature and so on. Let us put them on the same plot and see how they hold against the hockey stick. And here's all the papers we found. And you can kind of see they follow this curve. So typically in the literature, if you read this paper, for example, it will say, well, I really beat this guy here because of my method. But in fact, it's really because of aggregation. Now, how do I explain this? It's a very simple explanation. Suppose your behavior is the following. Every day, I select a pattern that I consume. And then, because I'm not perfect, I add some noise. I have some uncertainty about how I consume that pattern. Okay? This part of the curve, as I aggregate more and more people, that noise gets canceled. Okay? It flattens out because the pattern that I consume may not be explained very well by any one function that you use. So it's kind of the bias. So here you have variance, here you have bias. But this posed a very exciting question for us. Individuals having storage, maybe not such a good idea. Whole feeder having storage, maybe not such a big advantage. So what is the right group size? So we start asking ourselves questions of the following type. How should we price electricity? Can we group people together and price it separately? How should we install storage? And so on. Okay? So just to end here, future and ongoing work. As I said, we are looking into how to price electricity based on this data. We have some exciting new results that we just submitted. We can also use this type of data to aid in the design of microgrids. For example, how many people you need to have so that I can have a good forecast and use storage is an example, simple example, but you could go more. We want to learn improved behavior models. So on 2 ways. One is this idea of selecting patterns. Seems to be very consistent with psychology literature and the data. And the second thing we want to do is, for example, also be able to measure things like occupancy, the amount of shift that you can provide, and things like that. And the last 2 parts are, we are actually experimenting with some of these methods at PG&E, as well as other partners, where we are trying it on their actual programs to see, are these features any good? Despite, this being the first paper or set of metrics that were proposed that's totally data-driven to estimate all these types of flexibility. And the last thing is, we are now obtaining very high-resolution data. So maybe 500, 600 homes where everything is measured, appliance by appliance. What can I say about the behavior of these homes, and how does it affect pricing and all of these schemes? So thank you very much. I hope you enjoyed the talk.
Okay, great. So questions, starting with the students. Okay, back over there. Yep.
Just how valuable is storage? Because I've always heard that storing energy is pretty expensive.
Storing energy is valuable, but the value depends on three parameters. How much variability you have in the supply and the cost of that variability, how well you can forecast your consumption to add the storage, or how well you can forecast your generation, okay? And third, the storage technology itself. So there are circumstances in which you can show storage is not going to have a huge value. Even I think Sally wrote kind of a paper like that. But storage has one very important role. It allows you to move energy over time. And the value of power is not just the kilowatt hours. Power is three-dimensional. It's when you consume, how much you consume, and how reliable is that provision of what you're consuming. If I sell you 1 kilowatt hour at noon with 50% chance of you getting it, that has a price. If I sell the same thing with 100% chance, that has another price. So when you make it multidimensional, then you can compute the value of storage. But it really depends on all of these factors. There's no universal answer. It's valuable or invaluable or not valuable, sorry. So.
Okay, another one. Okay, great.
In the slide that you showed, the demand response and the number of consumers that you need to provide specific capacity for demand response, you showed it per hour. Yeah, here. So how much, the slide after that?
Here?
Yeah, so how much overlap is there from 1 hour to the other? So if I need 3,000 customers from 2 to 3 p.m., how many of those 3,000 customers are the same between?
So here I showed, because I just wanted kind of an optimistic estimate, I estimated separately. Typically the overlap is 80%, but we have designed an algorithm that also selects across hours. Okay, so you can enforce that. This is a very good question, but what we see is there is a lot of overlap, but it's not. I mean, it's about 70 to 80%. Okay.
Okay, next. Okay, yeah, we'll just open that up to everybody. The gentleman in the back. Yeah. Yeah.
Hi, I'm Ryan Gargano from Genesis. You've given a great argument about segmentation. Wouldn't that lead into a microgrid where each one of those segments would be serviced by a microgrid, so you can tailor that demand response to whatever is locally generated?
The way I think about it is because they may not be, if you think of a microgrid as being physically closed, that may not happen. But there is an argument for differentiated contracts, differentiated pricing. So here's an example. One type of algorithm we have designed now designs the pricing plan for you based on the load shapes you consume and the people who are in your group. So if all of us have some nice load shape that does not consume any power during peak hour, maybe we should be allowed to pay less, right? So the advantage is because, so now you may ask, well, why do you still want to design kind of this constant price? There's a lot of recent work, even some coming from Stanford, that shows customers respond to average prices, average costs. They don't respond very well to instantaneous costs in electricity, okay? But that is my, so I think there is differentiation and really this notion of clusters or groups, which is kind of microgrids, but they can be dispersed physically, geographically. Okay, so.
All right, we have one up here. Yeah.
I had a question. In the residential, the air conditioning is a big swing. Were you looking at just individual houses, or were you also including apartment buildings? And I'm curious what the difference is.
It was both. The data itself does not allow you to distinguish between both because of anonymization. We are now working with PG&E in a way that we can actually use all of the information they have available. Unfortunately, it's pretty hard because, as you can imagine, this is very sensitive data. But we had both. And when you look at zip code level information, you can maybe make an argument that goes as follows. Typically, we see this air conditioning impact being bigger on zip codes where it's mostly homes and being lower in zip codes where there's more apartment buildings and so on. Okay.
Okay, another one. Steve.
Ram, I have two questions. I think maybe they're connected, but you can let us know. You've been remarkably successful in getting this data from utilities, but of course, researchers often find it hard to get this sort of data, and I'm wondering how you manage to get PG&E to share this information. The second question, utilities have a real tough problem nowadays. As customers put on rooftop solar, utilities are selling less product because customers are generating some of their own energy. But the utilities still need to provide spinning reserves and infrastructure, but they don't have the revenue to cover it. And I wonder how you think the utility industry can survive in an environment like that.
So for the first question, let me answer it in two parts. The reason I got the data from utilities was not, in my initial intention, was not to say how utilities work and so on. I had my own vision of how the grid should work as a distributed system with these small groups, and I wanted to verify that in the data. It was my surprise that the utility themselves were not using a lot of this information. The reason we got this was partly because we had an initial data set that we got from Google. We created some algorithms, and we showed a lot of analysis that these guys couldn't have. And then we negotiated for about 2.5 years or 3 years. So there was, even before I arrived at Stanford, they had started talking to these guys to have all the security and data security, et cetera, and all kinds of things need to be signed. Initially, they wanted us to have a, what they call a security personnel at the door of the lab, because I'm not allowed to put this data on the web. So the computers are not stolen. So we got over all of those things. So that's part of it. So the uniqueness of the analysis excited them. And now the collaboration got tight through joint papers and things like that. Regarding the second question, I really think, see, when you look at what's happening in Germany and some other places, even Ireland, I think the business models are changing. So utilities are not anymore on the business of providing you power and charging it. They are in the business of providing you services. One service could be balancing your solar generation. Suppose I have a lot of solar, a lot of renewables. I could provide the balancing services. And here's a simple argument, right? The forecasting is better when I group people together. Who can do that? Well, you need some type of aggregator. The utility could become that aggregator. Okay? So that can be a new way of thinking about these. And it's very different from what is there today. Okay, thanks.
How about way in the back? Yeah.
Yeah, every so often we of course have catastrophic failures. And I wonder if there's any idea of how often something would come along that, using this, when things would shift enough to give you some sort of catastrophic failure.
I haven't thought about that. Maybe the way to think about this could be the following idea. Suppose these loads could be moved around, and suppose I'm in a situation where it's critical I get 1 kilowatt. How likely I am to get it in a particular zip code or a particular area? It will require a lot of different tools than what we have, but you could start with these load shapes and start thinking on those terms. But it's a very good question. I think another interesting question that can be answered is, suppose I have a very high amount of penetration of solar. Okay, how much of that variability is directly absorbed by just the homes that are there and the businesses that are there, and how much actually exceeds that, and that can cause failures too. So you can explore that, but it's kind of completely open. I don't think people have looked at that with data. There's a lot of, even for this type of evaluation, there's hundreds of papers which start from models, economic models, theory, and optimization. The problem though there is, you don't really have a validation from the data, and when you start looking at the data, it contradicts a lot of what these models assume. So.
Okay, do we have one more question? No? Okay, all right, well, thanks.
Oh, there was one question there.
Okay, all right, one question.
I want to ask you about the peak data. Is that coincident peak or non-coincident peak data?
What do you mean by coincident peak? Of all the homes?
That's correct, with the system peak.
So what we did is, since we analyzed the peak individually per home, there's some guys who are coincident and some guys who are not coincident. In California, the peak is happening, I think, around 3 o'clock or so. And you can see there's only a smaller fraction of residences that have the peak there at 3 o'clock. But if you look at businesses, they have a lot of. One thing that I learned is, see, these are small and medium-sized customers. The larger customers, they kind of drive the big patterns that you see out there in the system. What these guys allow you to do is to adjust, to respond very quickly to these big driving patterns. And the big guys are all very optimized because it makes economic sense for them. They might have a guy in-house who optimizes the power consumption, like for Google, Oracle, or I don't know, the state of California, you know, all the office buildings, they have a person specialized for that. But you know, if you have a Starbucks or your home, you're not going to do that. You're not going to spend hours and hours going and figuring out what plans you should enroll, what technologies you should add in, and so on. So the idea is, with this information, you can automate some of that process, design new ideas around how to do that, and really use it to balance all this variability. I doubt these guys would cause, you know, an enormous impact, like, you know, shifting the loads from the Google servers. That can cause a definite impact. The peaks are all caused by businesses in the majority. Okay.
Okay, well, thanks very much.
Okay, thank you very much. Bye-bye.